Good day, everyone. We're looking today at part of the mechanics course in A-level mathematics. It's chapter 9 in the Pearson Year 1 AS book. We're going to look at sections A and B, or rather the sections that deal with exercises A and B. And these deal primarily with displacement time and velocity time graphs. So I've got two examples here. I've got an example here of a displacement time graph and an example here of a velocity time graph. Now, before we start these, it's important to know the difference between these two words: distance, which obviously you've been using for many, many years, and displacement. They use the same units of measurement, meters or kilometers or miles or inches or something like that. This one, distance, really is just how far you have traveled or the length of something. Displacement is a vector quantity. So we're looking here at how far you are away from a certain point. And in this module, we almost always deal with displacement. Although you might be asked questions about distance, like total distance traveled or something, but we're dealing with displacement, so we have to consider not just how far have we gone, but how far away are we from an initial point, typically the origin, but not always. We're also going to deal with the difference between speed and velocity. And once again, speed is a scalar quantity and velocity is a vector quantity. Units you'll be used to, they both use the same units, meters per second or miles per hour or kilometers per hour or something like that. But speed is just a scalar quantity, whereas velocity is a vector quantity. Velocity is how fast are you traveling away from or towards a certain point. And in this module in AS mathematics, we tend to be dealing with velocity in terms of from a point, away from that point, or back towards that point, or negatively in the other direction. Okay, so we rarely deal with any motion circular or going off at different angles. It's either there or back. Okay, so in our first graph here, it's a displacement time graph. You'll notice we use the letter S for displacement. For velocity, for later graphs, we can either use U or V, and the difference between these two will become clear in the next section, in section C. So let's have a look at the properties of a displacement time graph. In this particular one, I've got my displacement up the side where you almost always have it. I'm going up in tens here. I haven't put units. That clearly make sure that the units that are on your graph are your units that you're using in your answer. Typically, but not always, meters per second. You can easily have kilometers per hour, perhaps even miles per hour, something like that. Miles per hour. And I say miles per hour because the first section of this, what's happening is at time naught, for the first 15 units of time, let's say 15 seconds, I have traveled a distance of 30. And because you know that this is a vector quantity, and because of the unit we're doing, this is going away from a certain initial point. So we're traveling away from a point for 15 seconds, and after the 15 seconds we have traveled a total distance of, let's say, 30 meters. So the slope of this gives you an idea of the velocity. If I have gone, let's say, 30 meters in 15 seconds, then a quick calculation, if we go back to some year 10 or 11 physics, speed is distance over time. Then the distance traveled, which is 30, divided by the time taken, which is 15, gives you a speed, or in our case, a velocity of 2, and I shall put some units in here, 2 meters per second or kilometers per hour or whatever it is. So the slope here, the gradient, gives you the velocity. In this case, because it's going upwards, it's moving away from our initial point. In this period here, the displacement has not changed. So we can assume at this point that we are stationary. There are occasions later on you'll find when actually your displacement can be unchanged, but actually you are traveling. If you think about moving in a circle around a point, your distance from that point is always the same, but clearly you have a speed. But that's moving further on down the line. Let's come back to this topic here. So here we are stationary. So we're stationary between 15 and 35 seconds, so for a total of 20 seconds. So here we have a velocity of 2 meters per second. Here we are stationary. Here we're going back to our original point. Once again, the gradient can tell us the speed we're traveling at. You'll see because this slope of this is less than this slope, it's also a negative slope. So we're going to have a negative velocity, meaning we're coming back to the original point. But we can work out the velocity or the average velocity over this period here by doing the total distance traveled, which is 30, divided by the time taken. Well, that's 35, that's 60, so the time is 25, and that will give us 1.2 meters per second. Now careful here, this is a minus slope, minus 1.2. Often in AS and A2 mechanics, you'll be looking at velocities that are perhaps initially going up and then coming back down again. You have to make sure that you've established which direction is positive, typically upwards, so therefore downwards is negative. Make sure you get your signs right. So the velocity here is minus 1.2. So at the start of the journey, we travel for 15 seconds at a uniform velocity. This is a straight line. Our velocity is uniform. And then we're stationary. And once again, this is a straight line coming back down. Our velocity is uniform, in this case, minus 1.2 meters per second. Now we're going to look at a velocity time graph. At GCSE you would have probably called it a speed time graph. Many of the properties are the same, but again we need to consider that this is not just speed going in any direction. We're looking initially at a velocity in two directions, so forwards and backwards or up and down. We're not turning any corners, not going through any angles. So initially we're just looking at a really simple model. Okay, let's have a look at what's going on here. We have various stages of this journey. We've got this first stage and the second stage and this bit. And this bit here might be worth considering this in two sections. Down to there and then to here. And then this last little bit. Okay, velocity time. So our velocity started off at zero. Our initial velocity is 0. And in 5 seconds, we've gone up to 15 meters per second. Now this can give us another calculation. If my velocity is increasing, it means I'm accelerating. So we're accelerating for this bit. We're also accelerating for this bit. But I'm sure you can see our acceleration here is less than our acceleration here. Acceleration we give by velocity divided by time. So for the first section, this section here, section 1, it's 15 meters per second divided by 5 seconds. So my acceleration is 3 meters per second squared, or 3 meters per second. Section 2, carry on speeding up, but not as quite a quick a rate. Our rate of change of velocity is a little bit less, but we're still speeding up. So in section 2, we're still accelerating. And again, it's velocity over time. Now be careful here, because although we're going up to 30 meters per second, we only started at 15. So the difference, we went from 15 up to 30, from 15 up to 30. So our increase in speed was 15 meters per second divided by the time it took to get there. Well, this starts at 5 seconds, goes up to 20. So that's 15 meters. In 15 seconds. So our acceleration in this section here is 1 meter per second squared. Section 3. At the first graph, here we are stationary. Where the line is flat on a displacement time graph, we are stationary. On a velocity time graph, if we're flat, it doesn't mean we are stationary. It means our velocity is constant. It means we are not accelerating. So in this bit here, we have constant velocity, which happens to be 30 meters per second. We're going to consider this in one section, but I shall talk about it firstly to that point and then to that point. So section 4, we start off at 30 meters per second, and here we're slowing down until we have momentarily stopped. So we're slowing down 30 meters per second to 0, and I've done that in what looks about 7.5 seconds. But the line carries on. It looks like our velocity increases, but negatively. And what that means is that we start going backwards. So my vehicle or my bicycle or whatever it is traveling at 30 meters per second. I slow down, presumably by braking. I stop, and then I start going backwards until I reach a velocity of -10. So let's look at the deceleration here, or the negative acceleration. I've gone from 30 to -10. I'm going to call it acceleration. I realise that sounds a little bit odd, but we will end up with a negative value. So I've gone from 30 to -10. So my velocity has decreased by 40 meters per second over a period of, and that's from 35 on the graph up to 45, 10 seconds. So my deceleration is -4 meters per second squared. That's section 4. And the last section, section 5, at this point I'm traveling at -10 meters per second. So -10 means back towards my original point, assuming I haven't actually arrived there yet. And this doesn't mean I'm speeding up necessarily. It means that my negative acceleration is slowing down. So here I'm coming backwards towards the original point, and I'm speeding up as I do it, and then still coming back to the original point, but slowing down. So here I've still got some acceleration. Nice if I could spell. Gone from -10 to 0, so 10 meters per second in 15 seconds. So 2/3 meters per second. So that's how you can do some calculations about acceleration on a velocity time graph. So here, speeding up at quite a quick rate, still speeding up but at a slower rate. Here I've got a constant velocity. Here rapidly slowing down till I reach 0 and then coming backwards. I'm still at this point got a negative velocity, so I'm still coming backwards, but my acceleration is slowing me down. Now there's another very important feature of a velocity time graph. And that is the area underneath the area underneath the line. You may remember from GCSE on rather simpler diagrams than this, you worked out the area underneath the curve of a velocity time graph, and that told you the total distance travelled. Now on this one here, we're going to have to split it up a little bit. So I'm going to work out the area under these four parts first. So the area here is the base times the height, and half it's a 5 times 15 is 75. The area here is 37.5 meters. Here I have a trapezium. So you may remember A plus B divided by 2 times H. This is a sideways trapezium. I'm sure that hasn't escaped you. So that's 30 plus 15 is 45. Half that, 22.5, times by 15. 2 buttons on my calculator. 22.5 times by 15 is 337.5. So the distance travelled in this section is 337.5 meters. Rather easier one here. That's 15 times 30. That's 450 meters. And this bit here, I'll need my calculator again. Base times height divided by 2. So this is 7.5 times by 30, and then half it. So my total distance here in this bit is 102.5 meters. I'm going to carry on and do the same thing for these two areas here. So this is 2.5 times 10, which is 25, half it, 12.5. We'll talk in a minute about what this means if it's below the line. And the last section here, this is 15, this is minus 10, or let's just call it 10 for the minute. 15 times 10, 150, half of it, 75 meters. So the distance I have travelled, is 37.5 plus 337.5 plus 450 plus 112.5